also, of course, your thoughts on where we are in the AI industry as such. And I think as this is the last of the talks in the webinar series for this batch of Sabudh students, I think the title is very apt as they move on from competing in Kaggle competitions and academic competitions to going out there and hopefully working in the enterprises that are using AI. So thank you again, and I'll pass over to you. Look forward to hearing your thoughts.
Thanks for the very generous introduction, Saurabh. So this is about when AI has to get real beyond the classroom. So first of all, let's be very clear about what are intelligent products, or what is our intent in creating intelligent products. So generally we think of human intelligence as finding the most efficient way to realize human goals, and typically involves discrimination of what paths are positive versus negative in progress towards the goal. Now, all of us know if a goal is not well specified, any path will take you there. That's what the Cheshire cat told Alice in Alice in Wonderland. Alice says, "Which road should I take?" And the cat said, where do you want to go?" So Alice says, "I don't know." So cat says, "It doesn't matter then what path you take." So it's very important that in creating industrial solutions, the goal is well specified. If it's not well specified, we need to go back to our leadership and make sure that we get that goal well specified. Now, the old definition of machine intelligence that you will find in Stuart Russell and Peter Norvik's textbook, which many of us studied, is basically find the most efficient way to realize machine goals, which could be pre-assigned by humans. And you continue executing even if you contradict emergent human goals, as in if you find out that there are some other goals, you just ignore it. The new definition for machine intelligence, which I'll acknowledge Stuart Russell for that, is to find the most efficient way to help humans realize uncertain human goals or changing human goals. And you keep checking if the goal has changed. Now, what is the upshot of this? What does this fundamentally mean? What this fundamentally means is that we need to create AI, which is not super AI, at least for now, but we need to focus on this enterprise AI, which is also called in textbooks as narrow AI. So these are systems explicitly designed to solve specific, reasonably well-defined problems. These could include games. It could include, Google Photo, or it could include Siri. It could include automated driving systems. Now, many people worry about these things, about AGI, strong AI, human-level AI. So this is all very beautiful, but we don't have too many clues yet about how to create such systems, where you train a chess program and it learns how to, for example, figure out attrition of employees in an enterprise. We haven't figured out such a system, or even some clues to such a system. And then, of course, if you have a general purpose learning system, it can become super AI. Now, of course, the thing is, the predictions about these things are 30, 40 years in the future. And generally, my rule of thumb on that is, if people make predictions or experts make predictions which go beyond their lifetime, take that with a huge grain of salt. So with those super AI stuff out of the way, we are focusing on the narrow, call it weak AI. I am a practitioner of weak AI, in case it's not clear. Okay. So now there are strong things you can do with weak AI, such as, for example, recently a real scientific grand challenge was solved, which is protein folding. Now, when I was a graduate student, so that's 20 years ago, this was considered extremely difficult to solve, and nobody thought it would be solved in their lifetime. Right? Now, people have done very careful science of the domain, and not just deep learning, but very careful science of the domain to get it to a score of 90 or above, which was practically not thought possible. I'll not go into the details of this because we have to focus on the enterprise AI part. But if you like, go look this up if you haven't already, that these guys have gotten structures down to an average error of 1.5 angstrom, which is basically an atom. You can't get resolutions. Even physically, if you are going to do X-ray crystallography, you cannot get better than that. So people are doing good science of the domain to solve problems. Now, my claim will be throughout this talk is that if we do good science of any domain, whether it's human resource management or supply chain and so forth, we can create good enterprise solutions. Right? So again, going back to the theme that AI products must amplify the human users or help the human users, right? So you might have data coming in from structured databases, transactions, you have sensors, you have news, tweets, Facebook, SMS, emails, blogs, video, audio, all kinds of stuff coming in together. And somehow or the other, along with the sensor data coming from Internet of Things, you need to help user make a decision about what they need to do. Now, I want to highlight some key things about this structure. So at the very bottom is what you would call the physical world, things which we objectify in nature, right? Could be elephants, could be cats, could be mountains, factories, computers, phones, anything. Right? Now, people sense these things and people manipulate these things. So people, have these abilities. Cognitive senses are cognitive. Acting, doing is cognitive ability. So we can do vision, sound, touch, smell, taste, measurement. In the acting space, we can do locomotion. We can do locomotion in traveling, or we can do locomotion from web page to web page. We can join networks, leave networks. We can manipulate things. We can construct, destruct, work, click. We can ingest things, buy things, consume things. We can recycle things, waste things, or create waste. We can influence, example, social networks, for example. Okay. So we can do all of these things, and these act on the world. Now, all of these have been digitized, right? So you sense these stimulus. So there are hardware sensors, software sensors, and there are all kinds of human inputs, as we already discussed, of news, tweets, Facebook, etc., etc. Often these are in the category of communication, which is, when coming from humans, speech or natural language, or they're trying to educate or change the knowledge of others. Now, a lot of what you see in machine learning today occurs at this next level, which is creating models for interpretation or seeing or analysis. So all the vision systems you have, automated speech recognition, natural language processing, digital signal processing, all of this is at this level where you are essentially seeing. This is the sensing level of the machines. Right? And then one can talk about what does one think about the world? What is the state of the world? In other words, if I am trying to manipulate a certain world, what are the most important variables in it, and what do those variables mean? And then one can talk about a further higher level where one understands the relationships between those variables. As we learn in physics, for example. Right? So there are causal relationships. You heat something too much, it melts. If you cool something, it freezes. Right? Those very simple things. Right? If you don't give good customer service, the customer goes away. If you perhaps reduce the price of your product, they may still stay. Right? Now, these causal relationships can be informed by the data as it's coming up from the bottom, or by domain knowledge which we already have, which comes from the people. Now, these relationships and the state representation of the world can be used to create models for prediction about what will happen in the world. So, and what you really want to know is what happens if I change something in the world, because that's going to inform what you want to do. So the act part of the people will be informed by these prediction models. And you do want to figure out, when you create these models, why the world is this way, not that way, or it turned out this way, not that way. Right? So those are called explanations. Now, once you have these kinds of models, now you want to worry about controlling the world or changing the world. Now, how much we are successful in it, that's another thing, but we try anyways. So now in this, something very important needs to be noted, that you may create these models for prediction, which may be based on many input variables, and some variables that are not in the input set. Right? So those may be intermediate or hidden variables. Now, the thing about these models is not all the input variables are controllable by humans or controllable at all. Right? So, for example, the weather is not controllable at all. So if you're going to create a recommendation system which did not take where, for example, you're selling umbrellas and you did not take weather into account, then you will have a problem. So one needs to, when one creates a control system to try to figure out what to change, it is somewhat obvious that you need to control the variables that you can control. And then you need to, you can say, address the issue of what you cannot control. So now how do you control? You figure out what if. You create these models and then you run simulations with different variables of the inputs, with different values of the input variables, and including counterfactuals. What if this did not happen, right? Those kinds of simulations, you run those and optimize over those simulations, and perhaps you may have multiple objectives within certain boundary conditions. That the world is not changing, you're thinking the world is not changing, and within that you say that I control the objective, and I try to optimize for that. Now, the world does change, as you might imagine. This assumption doesn't always hold, so one may have to do this adaptive optimization of objectives when the boundary conditions change. And then one may have to retrain the models depending on how you want to reinforce for the objectives. These kinds of systems can create decision support systems which can give input to people to act in certain way, do certain things to the physical world, like factories, computers, phones, or other things that we objectify in nature. Now, beyond these systems are, is the area where Saurabh has expertise in, where we create recommendation systems for people, or models predicting people's behavior or actions. Now, these are particularly difficult compared to things like, modeling what's happening in factories or computers and so forth, or even vision systems and so on. And while we may use these things, but creating recommendation systems or predicting people's behavior or actions is fairly hard, because in a lot of the bottom-up approach that we saw here, the assumption there is that a lot of interaction between variables is rational or reasonable. However, people can be unreasonable or irrational. So therefore, creating such models is particularly difficult. So this is the big picture of how we are trying to solve problems. What is the approach we are taking? Now you might say, well, I'm going to solve all the problems in the world, but this is what we think of as machine learning use cases. Typically multi-year moonshots, which are funded by tech giants. So you have internet scale, general purpose media interpretation, like image identification, language translation, and so forth. Okay. Now, notice that these, in the previous diagram we put this at the very bottom, at this level, models for interpretation, seeing, analysis, even though these are grand challenges. There is often large volume of label training data in these kind of problems. And we often are confident that the training set effectively represents the full distribution of observations we'll see in production. Now, unfortunately, in the field, very often this observation is violated. This idea that the distribution of the training, of the test set or the validation set or the production set is going to be the same as what's the training set. Often training time and cost is not a strong constraint in these huge the moonshot kind of problems. You might have a big network of GPUs, TPUs available. And often the goal is to provide fully automated decision making. And one might be able to create completely novel algorithms developed by a dedicated team of ML researchers. Now, this is only a small part of what's needed in the enterprise. Now, enterprise use cases actually look very different. And I'm talking about ordinary enterprises like the ones I work for, and a very large number of enterprises which are not directly things like Google or Amazon, for example. Often your training data is very limited. It may be a mix of labeled and unlabeled data. It's not initially clear if training data represents the full distribution of what you'll see in production, or it's even representative of what's in production. One needs to apply many, many different techniques, not just one or two techniques. There are specific time, cost, and resource constraints. You need to solve a problem within a given time, within a given amount of money, which means you have a certain objective to fulfill. And often you need a decision support system rather than a fully automated decision making system. So you might say, well, I have solved chess, I've solved Go, I have a system which automatically solves games. What is this little enterprise problem? So let me tell you what it is. Well, the challenge is with games and all, the problem statement is very well formulated and it's very well formulatable. In the case of enterprise problems, the problem statement is often not well formulated. It requires careful science of the domain to even formulate the problem. And deep domain expertise makes a huge difference between creating a toy system versus which will be brittle in the field, of course, and an in production high value system. The goal is often not clear and it needs to be determined and carefully specified, which means there needs to be sort of very careful dialogue, very careful discussion, very careful documentation of that. And often the questions that the models need to answer are counterfactuals, which means you may have to say, what if this did not happen? Now, that may not be in your data at all. So therefore, you need causal models. And the last thing is that the rules of the game, which is the relationships between different entities in the enterprise, and the board itself, which is the domain knowledge, these are not known or well represented in the enterprise. In the games, these are fully known usually. So there it becomes a little bit easier. Another challenge with the enterprise is, versus games is, in games you can play against yourself. Now, an enterprise cannot play against themselves. It's too risky in real life. And we'll come to this last part, the data generation part. Then there's further problems with the enterprise problem. One is there's a lack of direct feedback. So if you're on a Kaggle leaderboard, the leaderboard tells you how well you're doing. Now, in the enterprise, there is no leaderboard. You're your own leader. You need to determine when you have actually solved the problem. Data is often not predetermined. It's not even pre-collected. It's not even pre-cleaned. You clean it. So that's a very important one. Often the data cannot be generated on demand. You cannot just say, like for example, with games, you can generate the data on demand. In this case, you can't. Right? The data is what it is. Often statisticians get on the case, and I used to get on the case of many colleagues that, if you are doing an analysis after the data has already been collected, you have killed the experiment. You have to design the experiment properly with a full factorial design or perhaps a fractional factorial design, proper design of experiment. Then you collect the data and you find out what's affecting what. Now, the reality is those experiments get very expensive outside of pure science, let's say biology or physics or chemistry. So in the enterprise, you do sometimes get to do experiments, but very often you're given operational data, right, which may not have all the sources of variation you're looking for. That's another challenge. And the last one is your data changes. So your test set is dynamic, your training set is variations in input. You can get good model metrics if you just summarize variations in input with very large model. That's going to be brittle in the field if you're not model the process. And again, in the enterprise, you need end-to-end automation. Of course, that's that goes without saying. And last one is the operational story in the enterprise is different. One needs to work with people, and the models need to work with the people. So, for example, if everyone sees a certain recommendation given by a certain algorithm, there may be a liability of an action or inaction. For example, if I create a system of a financial system which tells my CEO that you're going to have a bad next quarter, and I may give certain recommendations of what they should or should not do. Now, if they see it, they're liable. If they don't see it, they're still liable. So that becomes a challenge. Not everybody can be shown all recommendations, especially if the model is good. If the model is bad, nobody needs to see it anyway. We need to convert nearly all outputs to units of vitamin M, as in money. Because the decision making is often in enterprises based on money. So a certain recommendation or certain output has to convert to money. One needs to worry about behavioral psychology because people nearly always find a way around KPIs, surveys, sensors, or AI based systems. As you can imagine, many of us have sort of figured out, as Google has changed, for example, we have figured out how to give it queries that would create a desired result. Now, often the interventions and analysis in enterprise might be driven by irrational choices. So people can figure out ways around your AI system. The last one is the engineering and scalability can kill you, and the constraints of time, memory, compute will matter. So let us look at another part of this, which is what does it create? What does it take to create such systems for the enterprise? Now, I'll pause here for a minute and see if there are any questions before we go on until thus far.
Nothing at this point, Vikas.
Okay, we'll keep going. I've just stated the problem right now. No solutions yet. Okay, so what does it take to create such systems? Well, so here's what you're taught in textbooks, in schools, in universities. You have some training data, you have a learning algorithm, you create a model, give it a runtime data and predictions. So does anybody disagree with this? Is this what often is taught for supervised learning anyway? Now, in the real world, even for just one model, things get very, very complicated. Your raw data may need legal review. Can you even use it? Can the customer even allow to be used? Your sample may still need to be annotated. It may not be annotated. You may need to crowdsource the learning. Sorry, the annotation. There might be features extraction steps needed for everything that the deep learning story tells us. It still occurs at the leaf level on the diagram I showed you previously. Right? It occurs at the lowest level of models. So for creating the enterprise scale models, one will have to do some feature extraction, the old school AI way. And one may have missing data in certain important areas. So for that, we may have to do active learning to figure out where we need to get more data. Right? And again, with the model, even if you have a model, you will still need to do interpretation, and the interpretation has to be such that it is interpretable by humans and they're willing to accept it. Right? And then there are issues of visualization, error analysis, reinforcement learning, customer feedback, incorporating customer feedback, etc. So this is a typical, and this is just one model. Just one model. As I showed you in that previous diagram, there could be several, scores of models. Some not just that. So this is just for the machine learning model. Not just that, your ML story is just the centerpiece here. The little green one. This is from a paper from Google, the hidden technical debt in machine learning systems. And this is something we encounter as practitioners every day, that you have to look at the configuration, the customer configuration, the infrastructure configuration, all of that you have to worry about. You have to worry about data collection, you have to worry about data verification, how good is it, how bad is it, what does the distribution look like. You have to worry about the infrastructure, machine resource management. You have to worry about analysis tools on top of the ML code. Now, a lot of people come out and say, you know what, I can just throw some data at some set of functions and find some nuggets serendipitously. That's my enterprise AI. So what I say to that is, if you have that kind of money lying around, let's talk. The real challenge is that even for well-directed, carefully designed systems that are purely data-driven, there are problems. The models may not capture underlying data generating process. We alluded to this earlier, that you may be just mimicking data IO, but you're not actually capturing the Now, that's something that's not in the data. Often therefore the models are brittle outside data boundary conditions if they're purely data driven. And what happens is it tries to force the identification of new data into existing distributions without discriminative generating process. And so you are unable to answer causal questions, counterfactuals. Now you may not believe causation, which is the bottom level we saw in our big diagram, the leaf level that I mentioned. This is the level of what is called association or just seeing. All these prediction models, classification models, detection, recognition from images, video, speech, audio, text, tables, all of this time series, all of this is just at the level of association, which is you're seeing what is the probability of y given x. This limits us from reasoning about what new actions can we do, what experiments can we do, what explanations can I produce. So let's see. Now, how far can you go with this? What questions can we not answer? What questions can we answer? So here is an example of what we did. Right? So this is about coronavirus, I guess, by location. So you try to figure out if people are being discriminated against in hiring, promotion, compensation, termination due to their gender or ethnicity, for example. Right. So now this is an expensive problem. A lot of corporations pay millions of dollars in fines. So now the challenge with this is it gets very expensive, and one can produce category, whatever jobs they, somebody's a man. So total number of applicants, how many were selected, how many were rejected. And then one has to look at that. I can give you 60,000 rows of this data. Fairly simple tools can create, you can calculate, for example, the chi-square test can tell you, sorry, in this case, I'm showing you just a minute, the standard deviation, and this is not the regular standard deviation. This is the binomial. So what happens is you have people who are hired and not hired, number A, number B, number C, number D, and male versus female, for example. Right? Now, you can think about how many ways can you choose from A plus C males, total A plus C males, in how
Your voice seems to be cutting out, Vikas, every couple of minutes. Could you try getting onto your mobile network instead? Vikas had warned me that his internet was misbehaving yesterday. They had some big outage. Seems like he's still having issues there. Hi,
Hey,
Vikas. Yeah, sorry.
without being connected. Yes. When did you last lose me?
You had started talking about the Fisher exact test, but we were losing you for a couple of seconds,
Okay, so that's
every
for
couple of minutes.
Okay, let me try to reconnect. Just a moment. Just a minute. Sorry, I thought they had fixed the network. Just this moment. So
Do you
right
think?
now I'm on the phone, basically.
Oh, you are. Okay.
Are we back?
Can't see a screen yet.
No, I think I'm back on the network. Just a moment. I just have to reconnect to Zoom. Just a moment. Sorry about this.
No problem.
All of you. This should have. It's taking forever to connect. Now I can do something really crazy. I can show you my slides by the phone. Instead of seeing my face, you see the slides. This. Okay. This is probably not very good, right?
No, it works actually. Or do you want to hotspot can you connect your laptop to a hotspot instead?
That's what I was doing.
Oh, okay.
See, I think.
Okay.
Oh, hold on. Just a minute. I ended up joining as a participant on the computer. Just 1 minute. I'd reconnect that. Sorry. I have to look for the. Yeah, this is the right one.
Tavleen, you can probably just make Vikas's second connection as well.
Okay, sir.
Please accept my apologies. This is I wasn't expecting this. Okay. Like no internet. That's what it says. Okay. I'm going to do it the dirty way. Okay. Can you see my screen? Let's see. Yeah. Okay. Here goes my screen. Okay. Can everybody see my screen?
It's not very clear because.
Not very clear. Okay.
Do you want to reconnect from your laptop and we'll make that a co-host too, your second login?
Yeah, let me try doing that. I am. Okay. Disconnected. Okay. Now I switched the computer completely to this thing. Hopefully that will work. Okay, launch. Okay, I'm going to turn off the video on this and hope we can get this working. Okay.
Tavleen, can you make Vikas's second login co-host as well, please?
Yes, sir, done.
Okay, so I can share now. It says host disabled.
No, hang on. It's not done, Tavleen. There is a second. Yeah, perfect. Now, try that now, Vikas.
Okay.
Yes, perfect.
Screen should be visible now.
Yes, it is.
Okay. Okay. I'm sorry about this, everybody. I'm sorry.
Not at all.
Okay.
We
So
appreciate you
what I
doing
was
that.
telling you is, in the enterprise, interesting things happen. Now you might say, this is trivial. I can implement this in any language. Now, um, at a certain employer, I was asked to do this in SQL. And you know what I had to do? I had to go back to Srinivas Ramanujan's lost diary, find an approximation to the factorial, which is actually the gamma, sorry, approximation to the gamma function, which Srinivas Ramanujan had in his diary, and use that in the SQL to find the Fisher's exact test. So you might have to do these kinds of funny things sometimes in the enterprise. You don't always get to use Python or your language of choice. Now, what questions cannot be answered using these models, right? So we talked about salary and so on. I can find how much discrimination there is, right? But I can't tell you why was X paid less than Y, because I did not model the variables in the appraisal process, right? All I modeled was, all I had was how many people are there and how many people are getting more salary, how many people are getting less salary. That's all I have. So that cannot tell me anything. Or it doesn't even tell me that the company pays people a certain percent above their current salary for laterals, meaning internal employees don't get as much. Um, why are certain groups hired more than others? I can say certain groups are hired more than others, but why certain groups more than the others? I don't know. Because I did not account for the business process where most CVs from the application system are discarded in favor of employee referrals, for example. Now, I can't also answer the question, what if I shut down the employee referral process? Will I lose my best source of employees? Would I still ensure diversity? What if I required certain percentages of people in the applicant pool? What do I need to do? My model doesn't tell me that. So therefore, we need to go to this next level where you say, if you do something, what will happen? So that the lower level was probability of Y given S. So this is just seeing. So the idea is the probability of event Y, given that we intervene and set the value of X, which is the input variables, to X, while observing another event Z. So for example, what will happen to sales if we double the price of a product? See, that this question, one might think, oh, I have a price prediction, price to sales model. But the challenge is the past sales data cannot be used to answer this question in a genuine enterprise. For a school project, you can. In a actual enterprise, what will happen is there are customer choices that will change in reaction to the new pricing. The market conditions may not be the same as the past. Perhaps there was a higher price in the past and there were certain customer choices available at the time. So all of that needs to be taken into account in the model. Or what is the effect of prevalence of lung cancer if we ban cigarettes? Versus if you just observe that non-smokers who have a lung cancer gene also get cancer. Now see that the challenge here is, you may be amazed by this, but this data on lung cancer from cigarettes was available since the 1950s. But the statisticians kept squabbling over, does it actually mean that lung cancer is caused by cigarettes? So they did not have these kinds of models which would be able to tell you what is the probability of lung cancer given somebody smoking cigarettes, or if you ban cigarettes, what happens? So this was the work of Judea Pearl with the Bayesian networks, Bayesian belief networks, which led to solving some of these problems, for example. Another example of this could be, if I take aspirin, will my headache be cured? Or what would Y be if I do X, basically? This is about learning by doing. So to be able to do this, you have to be able to integrate signals from multiple sources. That's what we saw in the very first picture about that hierarchy that I showed you. What kind of integration would you use to be able to create these models? So here is another problem statement which we solved. This is a customer tone at an investment bank. So this investment bank has 2,000 large clients, each of whom exceeds $100 million in investment each. They have 10K to 100K end users, and it costs $20 million to replace a client. That's very expensive. Many times people make these customer attrition models. Now it doesn't cost this much to replace a client, but in this case, it costs that much to replace a client. So their challenge to us was, what can we do to estimate that the client might leave? And it doesn't help to tell you 3 days before or even a 1 month before they're about to leave that they're going to leave. You need early signals. Maybe you need to know 6 months, 9 months in advance. You need to have close to 100% recall on negative sentiment on this. Now, this is something I'm saying very trivially here, but we found this out painfully. So this is one of the things in the enterprise. Nobody tells you this. The customer didn't tell us this. What we found was that people who are managing $100 million in money or $1 billion in money, they don't send you negative signals very easily. They don't scream at you on the phone. They don't send you, expletive. They don't give negative signals to your customer service representatives. So, but if they are saying something, then you better get on it right away. So the challenge is that if you give equal weight to all kinds of sentiment, I'm using the word sentiment in a general way. It could mean numbers, it could mean natural language, it could mean anything. But the challenge here is, if you give equal weights, what will happen is that the positive signals will drown out the negative signals in this particular case. So for the problem, so the kind of model we create, the kind of metrics we choose, the kind of sort of selection of data we do is highly dependent on knowing this, right? And we did not know this for the initial 6 months of the project. So the initial 6 months of the work had to be thrown away, essentially, right? We found this out after working with the data for some time, that basically there was very, very little negative data, but if there was, we needed to pay attention to it. That's number one. Number two, we needed high precision to avoid wasting time chasing false positives. So the false positive would be customer is about to leave, right? Now, these are very large clients, and if you sometimes when you try to address a problem, you might end up creating the problem. It's kind of like the electron. When you try to observe the electron, you might change its position, or you could change its momentum. So kind of like that. So the problem statement here, based on the previous run, is the probability of event Y, which is customer leaving or staying, given that we intervene and set the value of X as fixed service issues, while observing competitors offering better products and no complaints at competitors. So we created this problem statement. This was not given to us by the customer. What was given to us by the customer is, what can we do to estimate that the client might leave? That's it. So what we did? We said, give us everything. Give us your KPIs, new accounts, transfer of assets in and out, assets under management, basically your entire database. Tell us what are your not in good order cases, cashiering, service recovery, trading in and out, structured interaction data, emails, phone calls, service center requests and responses, phone call recordings, call notes, all of this. Now notice I'm calling this structured interaction data because it helps you create graphs of interactions, for example. Right? Now within each of these, there is what you would call unstructured data, which we had to make structured. So for example, emails. Right? I'll share something about emails if we have time, but emails we found out have a lot of negative sentiment. 100% of the emails had negative sentiment. You're like, why is this? Why is this organization, or every single customer is negative? What's wrong with them? And what we found is, those footers that occur at the bottom of emails between corporations which worry about lawyers and so on, those have very negative language. You may not send this to anybody, don't forward this to anybody, this is secret, and so on. Right? Now, our sentiment analysis tools were picking those up. So we had to remove all of those. We have to remove greetings also, good morning and all that, because that was spoiling our signals. And so now, so that's emails or phone call recordings, right? So you can get sentiment from the, not just the words, but the tone in which people are speaking. And then you have notes, people make written notes, often text notes in the computer. So there are activity notes, firm notes, survey comments, web logs, pages visited, errors, performance, timeouts, activity logs, etc. And it's very interesting. A lot of people are after social media. I have been telling many of the customers that you will not find any social media data on your customers if your customers are B2B. Because if they put anything on the social media, they must be violating their contract. So I tried to tell this to our customers, they would not listen. So we said, okay, we'll collect the data anyway. And what they found was there was really no signal in the social media. Although it's very hip to talk about social media, and we'll get information from there. But what we found was there was very, very little in the social media. So this kind of just tells you that what you see out in the world, that, oh, let me get some information from Twitter or Facebook or LinkedIn and so on, and what you actually find for some use cases may not be the same thing. So I mentioned this to you that we had to figure out whether the customer leaves. Now the challenge there was that we had to include causality there because there was a certain behavioral psychology involved, which our models would not take into account. So let's say today there are lots of complaints. So you're on the left-hand side. So you have a lot of phone calls in your customer service center. There are emails highlighting issues. And then what happens is, okay, looks like my computer lost signal again. Just a moment. Just a moment. Okay, I'm going to disable. Are we back again? Sorry. Are we back again?
Don't see your screen.
Don't see it. Okay, let me see. Stop share. I hope I am connecting. Okay. So if I share again, let me see. Does it show up now?
Don't see your slides. They're coming up. Yeah, that's perfect.
Okay, let's try
Oh.
again. Okay.
Yeah.
Okay. Yeah.
So Vikas,
So what I was saying was, so you may have a lot of. Yeah.
So sorry, I had a question there. So when you were talking about emails and the footer actually having a lot of negative sentiment, would there also be a case that customers of investment banks would only write in whenever there's something wrong, right? I mean, they're never going to write to congratulate you on how well you've done. I mean, is there a skew there as well?
Yes, as well. Yes.
Okay.
So
Okay.
it was actually very interesting. Well, and also the negative things they say in a positive way.
Right.
I'll show you some examples.
Okay, great. Thank you.
Yeah. So it gets very, very interesting that if you don't look at the data closely, you may predict everything is negative, but it's not. So what we saw in their data was, so 9 months before the customer leaves, there are lots of complaints and all this. 3 months later, which means 6 months before they leave, pretty much phone calls go away, emails highlighting issues go away, no complaints. The VP on the account gets a bonus. Amazing, right? And the customer leaves. And you're like, what happened? So what happened was when your wife stops complaining or your spouse stops complaining. What that means is if your employee or if your customer or if your spouse is complaining, that's a good thing. When they stop complaining, that means they have given up on you. Now, that's what would happen. And the VPs were getting bonuses. So what we did was, we said, can I find out at this T-9 months point where things are wrong? And the problem with this is the KPIs all look good all throughout. In fact, when the customer leaves, at that time, the KPIs are the best. Okay, something is really, really wrong with this.
Yeah, we've lost your slides again.
Just a minute. I'm going to just disable my connection to the terrestrial network. Just run it off of the. Okay. So this is running off of Mukesh Ambani's network. Hopefully this will work. I've completely disconnected from the terrestrial network.
Okay. Best of luck.
Yeah, yeah. I hope we can get this to work. Okay. So now we were able to figure out that 9 months in advance that there is a problem, and most of the time when we were able to figure out, it was something in the phone conversations or emails. The numbers never told the story, anything about the story. So, and how did we explain it to the customers? We were able to say how extreme were their KPIs and sentiments with respect to the customer segment. We were able to show them key excerpts from emails, customer service notes, speech, voice analytics samples. And we could also show them locally similar cases which do much better, worse, or with similar outcomes. Now, I wish I could show you the emails, but I will not show given we have lost some time in doing this. So we'll go through this and say the results were we were able to estimate the customer tone accurately 86% of the time in production. So this was used by senior management to challenge the judgment of account managers and address the shortcomings early on, and it stopped many people's bonuses. That was the sort of highlight for that customer, that they were able to do that. Now notice, we still could not answer another level of questions here. We were able to say why a customer is about to leave, but we were not able to say if we had fixed only 50% of the customer complaints instead of, let's say 90%, would they have still been retained? Because we would have spent 70% less money. Corporations think about these things. What if we had been fixing only 80% of the easiest problems? Would that help us retain customers in the changing market? Or what if we provided better returns and still had website issues? Would the customer still leave us? Our model could not address that because it was still at the level of some causal, some association. Now, how do we create models to answer such questions? So that's the third rung of causation here. This material is actually taken from Judea Pearl's book, The Book of Why. Very interesting reading. Now, he doesn't give too many ways of creating such models, so I'm going to discuss some of that, how to create such models. So to be able to answer questions such as, what is the probability that Joe's salary would be Y had he finished college, given that his actual salary is Y and he had only 2 years of college? Now, this is the kind of question I want to be able to answer. Or, how likely is it that my exercise was a necessary or sufficient cause of his death, right? Or, for example, in a civil court, a defendant is considered responsible for an injury if, but for the defendant's action, it is more likely than not that the injury would not have occurred. So essentially, what was it X that caused Y? What if X had not occurred? What if I had acted differently? So this is the idea of imagining, retrospection. So you use this for science, you use this for legal reasoning, you use this for what if simulations. So now this is going all the way back to my doctoral work, and I'm not going to bore you with the biology, but what this shows you, this is a plant cell, or my cartoon version of a plant cell and my cartoon version of a bacterium, which is attacking the plant cell with a virulent protein, which is attaches to a resistance protein, and that leads to a signaling, which leads to this cell dying. Now you might say, wait a minute, it recognized and it died. That doesn't make sense. Well, what's happening here is that the cell is kind of philanthropic, or you can say self-preserving in one sense, because it kills itself so that its neighbors can live. That's the idea. So its killing will release certain chemicals, which is going to sort of reduce the growth of bacteria. Right? Now, this thing can be represented by this causal network. Now, we had no idea which of these arrows in this network actually existed when we started off this research work. We had no idea which one, so some of these, the ones with sharp arrows at the end, are positive feedback and or positive reaction, and the ones with the blunt edge are negative feedback. Now notice, and these cuts in the middle are changes which, or mutants which can stop that change. So of course, some of these things may be new to this team here. So I'll just mention some of these things. So hydrogen peroxide is one of the things they release, which really gives a hard time to the bacteria. Salicylate is another thing that really helps the cell sort of deal with this. Now you might imagine the salicylate is aspirin, by the way. Methyl salicylate is aspirin. So it works for humans. Apparently it works for plants too. Now we have to figure out how well does it work. How well does it work? And if we can improve this if we can improve this network in such a way that it can improve the plant resistance to the bacteria. So the way this was done was with a set of delay differential equations. The delay differential equation just means that certain things, like certain arrows here act after a certain period of time, which we don't have a very good model of. One could have written a partial differential equation based model. Now, even here, certain interesting things happen. I mentioned, there's time constraints. Now, this model would take about 10 days to run on the state-of-the-art hardware of the time. So I had to figure out how to run it faster and had to get a 150-fold speed up. And this professor, Dr. Lawrence Champagne at Southern Methodist University, this guy was so nice that I sent him a little algorithm of how to speed up his algorithm in MATLAB. He worked overnight without waiting for his grad students, and he worked actually not just overnight, over the weekend to send me a 150-fold sped up code. So this is another thing you have to do in enterprise, that you have to make sure that your code can run in a reasonable amount of time, for example, when the data updates. Now, the way this was done was each of these arrows had a corresponding term in the differential equation. So, this red one is this red thing here. The black ones are the black arrows, right? And the green one is the green arrow. This is the green term here, right? So using these equations, one simulates how much programmed cell death you will get based on different variables, such as this hydrogen peroxide, superoxide, or salicylate. And then one can figure out what is the optimal location. So I mentioned optimizing the system, finding the optimal point. I've shown the plot here, but of course this will be done in an analytical, not analytical, but if you can just compute what is the optimal point, right? So, and again, this was extended to cell division and differentiation as well. This is how the equations look like. Now, this obviously is not something that's put in production, because this is simply a research system. I'll show you something that was actually put in production, which was using a similar system of equations, much more complex system of equations, for which case I cannot show you the equations. And so therefore, I showed you the equations in that one, and here I will just describe what was done. So this is the semiconductor industry, where the process is very tightly controlled, right? So you detect there is a problem, diagnose the problem, mitigate, right? And from the signals, you predict what can be done, do the prognosis, and do anticipatory control. Okay.
I think your slides are not updating.
A hard time. Yeah, so that has to do with Mukesh Ambani network not updating. Okay, now can you see it? Coming up.
Yes, thank you.
I'm sorry for giving you this hard time. I don't know. Okay, right. Yeah, so I was talking about this being able to control the process. So what happens in the semiconductor industry is that you have these fabrication factories, fabs, and you want to be able to figure out how long your part will last in the field. Your semiconductor chip, how long will it last in the field, depending on how it's used and how it was fabricated. So the particular problem here was that there was a certain chipset from a certain company who we shall not name. And let me just show this, right? So they needed to save money, the OEMs like Dell and HP and so on. And the marketing specification said only cool the CPU chips. And the chip design spec said the current chip is not a CPU. So it would not be cooled by most OEMs. Now, this was extracted obviously using natural language processing. And then the thermal specification says cool all chips over X watts. And the current chip was over X watts. So that said current chip must be cooled. And as you can imagine, uncooled things are hot. I think this is my slide not update. Hold on. I am connected. Okay. Okay, I'm just going to continue until this thing comes up because I can talk through this. So if you don't cool something and it's getting hot, it gets very hot. So those chips would run hot in a lot of cases because they would not be cooled by the manufacturers. Running hot also implies very large temperature swing. You turn the thing on or off, it'll go through large temperature swings. Large temperature swing means this chip will go through larger temperature swings. Higher temperature differences cause more fatigue. In any mechanical system, there is this coefficient of thermal expansion mismatch, which we studied in high school. That coefficient of thermal expansion mismatch will stretch some layers more, some layers less. So there will be huge mechanical forces. So these chips will fail at higher rates. Not just that, the current operating system will create a lot of heat cool cycles because of its sleep states. So those also cause fatigue. So that will make it fail at a higher rate. And it has smaller joints. They'll also fail faster. And this chip has smaller solder joints, so it'll also fail faster. Now, these come from, by the way, finite element models. And in the lab models, the temperature assumed in the field for the small chips was some Celsius, 50 Celsius. And the current chip was a small chip, so they use a certain temperature in the models. The challenge was the actual temperature would be higher. The models were run using low temperature, so the models predict no failure. So there was this undetected contradiction in the human system, which was caught by our model. So we said, okay, the model says the fix will cost $50 million, but no fix was provided. So that would lead to risk of recall and brand loss. Yes. Was there a question?
No, because I think it's just $100 million.
Okay. Okay. So now notice using multiple things, right? You have facts extracted from documents, statistical trends, correlations using semantic extraction and inference, reasoning using an inference engine to draw conclusions, multiple sources of confidence using statistical and machine learning techniques. And at the leaf level, you have these deep learning models with predictive analytics, quantitative and symbolic reasoning, all of that to create this prediction that there's going to be a high failure rate for these parts, right? Now, this can be done in many, many fields, and is being done in many, many fields in pharma, in manufacturing, and so forth. Now, it's harder to do this, for example, in an area like recommendation systems for humans. And generally, it's harder to create things which create models which predict human behavior. But where you have some kind of an idea of the domain, it's easier to create such causal models. So it is kind of selling ourselves short if we don't create such models where some of the problem is known. So therefore, we do need dynamic causal models in the enterprise to go above the level of association to intervention to be able to answer counterfactual questions. That is a summary version of my presentation. I expected this to be more interactive, to say, how do you solve this kind of problem? How do you solve that kind of problem? And let me go back to my big picture slide here, which talks about all these topics in one place.
Because in fact, I mean, something that was coming to my mind was that some of the problems. some of the problems that you were talking about here that you're trying to solve, I mean, how do you even evaluate how correct your answer was, right? Because, I mean, there was a question on, what would Gandhi do if he hadn't been killed? How would we know whether what prediction we are making is even correct?
Okay. So that one is just an illustration just to show what kind of question. I don't think one would have at least right now, we don't have a model of those things.
But I mean, with human, models that are trying to, model human behavior, it is impossible, really, right, to know. Even if we talk about the example that you were, referring to about the investment bank, because there isn't the possibility to try out an alternative with the same human. How would we ever know whether, correcting 80% would be correct, right? Would solve the problem.
You would not know. You would not know. You would not know. All you could do is look at the past and see if my future will continue looking like the past.
Yeah,
and,
but
for the best. That means that is the limitation of the.
Right. Because we come across a lot of people in industry, doing A/B tests where they do an A, for a month and then do the B a month later. And which is, intuitively to me, completely the wrong thing to do, right? Because the world has changed a month later.
Yes.
So even that kind of look back doesn't really work, right?
It doesn't really work. Unless one has a real understanding of the causes of things.
Right.
Example, the example that I showed with protein folding. Right? Now, those people did not actually have an understanding of the causes of the folding, but what they did was they took all the little pieces that make up a protein, and they said, let me sort of create a scaffold of the protein from that. Right? So they actually didn't understand it at some level, but they broke down the problem in such a way that it appears as if it understood.
Right.
For example, in this, again, notice that it's a physics-based problem, that one. It is not a human-related problem. Human-related issues, I have had a lot of challenges unless I have a signal. So I'll give you a classic example of that. The classic example is every single company I have worked for, they have asked me to create a employee attrition model. Some of people just like that. And every time I tell them that you will never have the real data that is needed in your database. The real data that is needed is what is the person's interaction or engagement with their manager, what is their relationship with their manager. I mean, you can get it from emails, you can get it from, maybe SharePoint or Confluence or something. But really to find out what the relationship is, it's very hard. Right. And even then, somebody may leave for a totally different reason. So, similarly, it's one thing to predict what I'm going to buy on Amazon or what I might want to buy on Amazon, right? But it's totally something else to say whether I'm going to, leave a company, for example, or whether I'm going to choose to work at a certain place, or whether I'm going to be very successful in the job that I am in. So, for example, IBM has a model like that, which is quite amazing. They have that, right? So they'll give you what is the probability of this. They'll let you upload a resume, and then tell you how successful will this person be at this job. So quite amazing.
How accurate is that?
Somebody can do that. So I'm going to reserve my.
Yeah, you're being streamed live on YouTube, so you may want to be careful what you say.
Any other questions, comments, concerns?
Yeah, so I mean, from my perspective, I mean, I think you've kind of referred to this in any case, but the ability to reason the way you're talking about would require us to have a better understanding of the domain, right? And in most cases that's not available. So
Yes.
are we saying that the current pursuit of building models using data is flawed and therefore we should not be doing it? Or what is your take on this then?
So my take is it's not one or the other. So where we have an ability to learn from the data, we should do that. However, we should limit the search space. So the challenge is if you only have a data-driven model, its search space is unconstrained, practically speaking. And what that does is you may get into, your model may get unrealistic predictions in areas where it has not seen data. So the simplest thing that happens by some domain knowledge is that, for example, you can create a model about how to increase the profitability of a company, right? And that model will tell you that if you reduce the cost, the profitability goes up. Right. Let's say you fire 10% of the employees, your profitability goes up quite a bit, right? But there's a boundary condition there. If you fire 30%, maybe your profitability doesn't go up, and if you fire 50%, it doesn't go up at all. Meaning your profit goes up for the next quarter, but the following quarter is doomsday.
Right.
So the domain knowledge can put those kinds of conditions. So I'll give you a simple example, right? A lot of people got very excited by what was done by Jeffrey Hinton's team with ImageNet on the ImageNet computation. But notice their idea of convolutional neural networks was rooted in how image processing used to be done.
Right.
I mean, at least the way we used to do it.
Right.
And then they were able to figure out how to train those models, which was their key contribution. You cannot just take any random neural network and say, okay, this will do well with images. And then they improved this further when they took the intuition from scene decomposition and created capsule networks. Now notice those have not worked so well computationally. They're not been as trainable. But the kind of models that have been more useful in the field are the ones that are kind of derived from some intuition about how things work or what relationships exist.
Right.
For example, the plant and bacteria model that I showed you, if I assumed linear relationships there, my model will just fall flat.
Yeah.
Right? If I did not have a network, that one thing affects the other, affects the other, affects the other, affects the other, meaning it's like a loop there, actually. In reality, it's a loop. So if I'm going to assume, and a lot of the models today are essentially linear models, other than deep neural networks or radial basis function-based models and so on. Right? And in the case where we have nonlinear models, those have unspecified nonlinearity. Meaning we don't know what nonlinearity is, we just get a good fit. And the challenge with those models is those are underspecified, which has been published recently.
Right.
So there might be 1,000 models which fit that data. And we are not picking the most passive. Meaning we are essentially going away from the idea of science, which included Occam's razor, which is that you pick the simplest model.
Right.
So the approach I am proposing is that wherever we need data-driven models, those should be data-driven. For example, at this leaf node, this where I'm saying models for interpretation, seeing, analysis, and in this vision, speech recognition, language processing, not understanding. At this level, it is okay to have models which don't really understand the world. But once you try to worry about making decisions about the world at a granularity that involves decision making, then you will need to understand why this interacts with that. The classic example of that I think of, or very easy to understand example, is the example that Shailesh Kumar gives in his Ola example. Right, that you may have a model about scheduling, or with a queuing theory kind of model, or you may have a model about pricing, or you may have model about matching cars to passengers, or drivers to passengers, and so on. Now, each of these models affects the other model. So you cannot just create like let's say a model which just puts these into like a bin and say, you know what, let's figure out what is the relationship between them. The thing is, the relationship between them, many of those relationships are known. Right? That if the demand increases, the supply needs to increase. If the supply decreases, then and the demand is high, then the pricing needs to increase. Right? Those relationships have to be pre-coded in for the system to work properly.
Right.
So it is unfair to expect a machine learning system to automatically learn that.
Right.
Or another example, very simple example, trivial example. I can send each one of you Tycho Brahe's data of the planetary orbits. Try deriving Newton's laws from it, using any machine learning algorithm you want. It's an open challenge. I can send you Tycho Brahe's data. The challenge is, unless you know that there is this G M1 M2 interaction and divided by R square, unless that is explicitly in your search space, unless that particular interaction is in your search space,
Yeah.
right, you will have a hard time finding that one.
Sure.
Right? So, so the thing is, you may have data like Tycho Brahe's data, but you may have very sophisticated algorithms, but if you have no understanding or not even a hypothesis about the world. So here is the midway path, right? The midway path is what we, for example, showed in that, for the bacteria example. The midway path is that one may have hypotheses about the world. See, the high path is, I have no hypothesis about the world. I throw data at some algorithm, let it figure it out. What I'm saying is that path is not going to yield enterprise quality results. There needs to be a midway path which says, I have, let's say, 50 hypotheses about the world. Or I can generate hypotheses. That's another thing. One can create systems which will generate hypotheses. I can create hypotheses about the world and then use the data to throw away some hypotheses or keep some hypotheses, which is literally what we did with those differential equations in for the plant and the bacteria, and also for the warranty case for the semiconductor industry. That we were able to remove certain parts of the network, or the data showed us that there is need for a certain arrow in the network, but there is a missing arrow in the network. So when you see a need for a missing arrow in the network, then you look for that and put that in the network. So if we don't do that, then the challenge is we do not understand the processes that are generating the data. And if we don't know that, then we are simply creating expensive IO systems, essentially. And if you don't believe me, I'll somebody who is a little bit better known than me. About this, right? So, for example, we assume that the test data is from the same distribution as training data, right? That is a sort of foundation of any pure data-driven approach. The problem is it's often violated in practice. This is Yoshua Bengio's slide, shamelessly copied from him. So this leads to poor out-of-distribution generalization.
Yeah.
Now, Yoshua says you have to consider relaxed assumption that the test data was generated under the same causal dynamics, but from different initial conditions. Now, what that means is, that means your model has to somewhere capture the causal dynamics in the system. So right now, you're meant to believe that machine learning models cheat by relying only on superficial statistical irregularities. They remain vulnerable to out-of-distribution examples. I didn't show this, but this is fun stuff we saw in another venue. distributional shifts, catastrophic forgetting, etc. So, and his thesis is that the humans generalize better than other animals thanks to a more accurate internal model of underlying causal relationship. Of course, this is debatable, but again, his view is that if we don't have that, then we will be creating models which are essentially relying on superficial statistical regularities, which, for example, we saw this example with X-rays, right? That these models are looking at whether the machine is portable or it has a literality marker, or it is looking at this scan signature of a specific machine rather than looking at lesions of the disease.
Right.
So those challenges are there. Now, if one creates a model which limits the search space, which says, you know what, you only have to look in the lung, for example, as trivial as that, right? In this model, as trivial as that, you could say, identify the area of the lung and find me problems in that area. Now, if you can find that, then I will understand that you have found something good, and don't focus on anything else. As trivial as that, one can figure out that, okay, this model is working better. And you'll be amazed that that's literally what people are doing. So if you see, there's a friend of a mutual friend, Bhiksha Raj, he has recommended this approach as well, that one has to go back and while one has many ways of solving this problem, but the only true way to solve the problem is go to the domain knowledge. For example, in image recognition or image classification, he says you really have to go back to the domain knowledge of the kind people used to do in good old-fashioned AI. So things are moving in multiple directions. So there is progress with deep learning, for example, but there's also progress in these attention-based models, the kind of Joshua Bengio is working on, for example.
Right. Interesting.
Right. If there's nothing else, maybe we can close.
Thank you, Vikas. As always, this has been an incredible talk, and it's a pity that we've had issues with the internet, both at your end and mine.
That's on me, Saurabh. That's on me. I thought it was fixed. My internet guy came in the morning. I thought it was fixed, but it was not.
Don't worry. We'll just blame Mukesh Ambani for it, right?
No, we'll blame Mukesh Ambani for making it work.
True. So you're on your mobile network now. So, but anyway, Vikas, thank you. I think what's great is for in your talks is the fact that you break down a lot of the myths that exist in the world today, and in this domain specifically. And I always appreciate that, and I'm sure everybody who's listening to you has appreciated that today as well. So thank you, and hope to hear from you again soon at some point.
Thank you all for your time and attention. I'm sorry for the I/O issues, and thanks for tolerating me. And Happy New Year
to you too. Thank you. Take care.
Thank
Bye.
you.